Okay. So from now on, you're on record, everybody here. So proceeding with the next talk of our CCE, Astro Missions, it is a great pleasure to present to you Silvia Bonoli. I think it's the first time that she actually does a talk at OM. Is that right?
I think so.
Okay, incredible. Should have done some.
You should have invited me earlier. I'll come one day also physically.
Yes, we can arrange that now and get the dates for next year.
Yeah.
So a brief history. Silvia finished her PhD in 2010 at the Max Planck Institute for Astrophysics, the different one from the previous talk. And did some tours, postdoc tours at the University of Zurich, Switzerland, 2012, and then in Stanford, 2012 and 13. And she joined the Centro de Estudios de Física del Cosmos de Aragón, CEFCA, the main institution of JPAS, in 2014, and where she became a researcher, staff researcher. And now, since 2018, she is Donostia IKERBASQUE researcher at the Donostia International Physics Center in San Sebastian. Silvia also is member of many large programs, missions, like WEAVE, Euclid, LISA, Athena, and of course JPAS. She has been deeply involved in JPAS, the black hole galaxy evolution work, and others. And she's currently a science director of the collaboration and led the publication of the first results of JPAS-like data, the so-called mini JPAS, that I'm sure that a significant part of the group here not just knows about it, but was also a co-author in it. And she's going to be talking about JPAS today. So I'll pass the word to Silvia.
So thanks a lot, Renato, for the introduction, and thanks for the invitation as well. Yeah, it's nice to be here virtually, but yeah, I count on visiting not too far in the future, I hope. Yeah, when things get smoother than yeah, with everything, right? Okay, so let me start putting things full screen. Let's see. Can you see well? Well, I count on seeing well. Okay, if there is any problem, please interrupt me. Yeah, so the talk now, it's we heard about X-rays. Now we move to the optical. So I'm gonna tell you about the JPAS survey, the universe in 56 colors. So actually, it's 56 filters. Well, this is a large collaboration. I will tell you in a few minutes, primarily between Spain and Brazil. So many of you are involved, and many of you have done very important contributions for this survey. So before I get into that, though, I would like to briefly advertise the institute where I'm now a member, a staff member. So this is the Donostia International Physics Center. Donostia is the Basque name for San Sebastian. San Sebastian, it's a small town, well, medium-sized town for Spanish standard, probably for Brazil standard, very little town, but it's in the north of Spain, next to the border with France. And the institute has quite some long tradition on condensed matter and quantum physics. But a few years ago, they decided to open a new line in astrophysics. So now we are primarily 3 staff scientists permanently here, plus George Smoot, who is a 2006 Nobel Prize recipient for physics, who is partially as a partial appointment with us here in San Sebastian. Particularly, I want to emphasize that we have every year open positions from postdocs, PhD students, postdocs, and also tenure track positions. So in particular to the graduate students there, if you are interested, if you have any research, if your research is also close to any of our lines, we do galaxy evolution, cosmology, large-scale structure, but also global cluster science. So if you're interested in any of this field, keep an eye that we may open position. We are actually going to open some positions soon. All right, so today I will primarily tell you about the JPAS survey. I will start with the motivation for the survey, what are its technical specifications. I will also briefly touch upon 2 other multi-band surveys, J+ and S+, because they're very connected. They're very, they're somehow the small sisters of JPass. And in particular, S+ is being carried out in the south, from the southern hemisphere, and has a strong participation from the UN. Then I will. Then the second half of my talk will really be on mini JPass, which is a very small data set that was somehow mocking JPass. Is JPass-like data. It's a small data set, but it's been extremely useful to prove the capabilities of JPass and span large, and we started to investigate what is the potential in JPass from galactic science out to cosmology. So, well, a bit of motivation, right, or general introduction. It's interesting, so if you, I have a bit of a theoretical background, so I like sometimes to start discussing about our state-of-the-art simulations. So our understanding of the universe is now so good that effectively, if we take some initial conditions which are dictated by, the cosmic microwave background, really, which is like some cosmological model, so a lambda CDM, cold dark matter model with cosmological constant, plus a GR, which is the main for, which is what drives gravity. And we put everything in a computer. We effectively get out, we can do a simulation of the universe to mock the universe and have a representation of the universe, which really looks like something, what we observe, right? So this is an example. These are now relatively old, more than 15 years old now. But this is an example of the distribution of galaxies in the sky along the redshift from the 2DF and the Sloan Digital Sky Survey, CFA, two Great Wall. These are different structures that have been observed in the universe already more than 20 years ago. And this would be what the simulated, this is the large Millennium simulation, a pure n-body simulation. And this is again the Millennium simulation zoomed in some particular region that really resemble what is observed, the distribution of galaxies as it's observed. So we know really that the universe very much looks like what we are, like we know what are the main drivers of the universe. Although, as I will tell you in a minute, there are still many details that are still missing of that. Now, even if we go even a step forward and we actually include in all the simulation also full treatment of the baryonic physics, so how gas evolves, how stars form, and so on, we even get out of the computer galaxies that really resembles the galaxies that we see today. A beautiful example here is this comparison. On the left, you see an image of the Hubble Deep Field, one of the deepest fields before JWST arrived. And on the right, the illustrious simulation, one of the state-of-the-art large hydrodynamic simulation that tried to simulate the universe, the dark matter component, as well as the baryonic component. And at a first glance, you see that they're very similar to the point that sometimes it's hard to distinguish between the two. And now we have beautiful JWST data. This is the Stefan's quintet from JWST on the left. And on the right, it's an image from the illustrious TNG simulation, another simulation, hydrodynamic simulation. And of course, we don't get as many details in simulation as we get at this point, especially with JWST, with observations. But it's really impressive, like what is our theoretical knowledge of how the universe works and how we can simulate it. But there are many still open questions. We are at the point of precise cosmology, so we have more or less a well-defined global picture, general pictures, but there are still some details that are missing, right? I mean, we know that there is, 75% of the universe, of the energy budget of the universe is dominated by what we call dark energy. We know that there is dark matter, but we don't know what dark matter is, and we don't know really what is the nature of dark energy. And even in galactic evolution, despite we understand relatively well the global picture of how galaxies form, how they evolve, what is the morphological transformation of galaxies, there are still details that are missing, right? Especially in the first phases of galaxy formation, how really galaxies get quenched, what is the relative role of supernova feedback or AGN feedback in the quenching of black hole, in the quenching of galaxies, sorry. supermassive black holes that play such a big role in galaxy evolution, we don't know where they came from, right? How they form in the first place. So all these questions, cosmology in particular, but also this side question also related to galaxy evolutions, have been driven the design and actually, construction of very major experiments, starting from the very famous SDSS to the dark energy surveys. Here I'm only showing optical or near infrared experiments. I'm not getting into, we just heard about the beautiful Rosita X-ray mission, and there are many others wonderful experiments at other wavelengths. Here it's a collection in the optical and near infrared only, and it's not even complete. There are many projects that have been designed and conceived to really search for this dark energy, primarily by looking at the distribution of structures, how galaxies distribute in the sky, or looking at also the clusters, how also clusters and groups of galaxies are distributed in the sky, and what is their dark matter content. Overall, we can divide these projects into two main categories, right? There are two different general approach with that one can take in order to scan the sky, right? You either take pictures of the sky or you take spectra of objects in the sky. So on one side, photometry, so taking pictures of the sky, you have the advantages is that you take pictures of everything, so you're only limited by what is the sensitivity of your instrument, what is the magnitude depth, the flux, the limiting flux that you can reach. You have no issues like fiber collisions. And you can probe, it's also generally cheaper, so you can probe larger volume and larger number density of sources. And this allows you to carry out experiments like gravitational lensing and also cluster science, right? These are some examples. This is an image of the dark energy camera. Here it's some weak lensing map from DES. So this really depending on what is the main cosmological experiment that you want to carry out, this is really, you have to choose whether you want to go with photometry, so have these advantages. With the negative side is you have poor redshift precision, because generally these pictures on the sky are taken only with a few broadband filters, so you don't have accurate redshift for your objects, the objects that you're observing. On the other side, you have spectroscopic surveys. So their advantages is that you're taking spectra of each object you're observing. So you have redshift, you have the full spectral energy distribution, you have the full spectrum of all your objects. So for example, experiments like the baryonic acoustic oscillation, so the clustering, how objects are clustered, grouped in the sky. In this case, from the Lyman alpha forest, the clustering of the Lyman alpha forest that was possible, that was carried out with the BOSS survey, was only possible because you have spectroscopic, because you could really have the full spectrum of all the quasars in this case observed, right? Now, on the negative side, as I said earlier, they're very expensive. And also, you need to pre-select your targets. So, you have to decide which objects you're going to observe. So you need to first take some photometric data, decide which objects you're observing, and then observe them. With often the problem that a lot of these objects that you have selected are not actually the ones that you wanted to observe. Now, what is in between is what we call spectrophotometry. So it's an approach that takes the advantage of both. So instead of taking a full spectra, high resolution spectra of the sky, of some particular objects, what spectrophotometry does is that you take pictures of the sky, but so not only of just one object, but actually a full field, but with so many filters that you effectively can reconstruct a low resolution spectra for all the objects that you are detecting. This has started already. This technique has been used for many years now. The first survey that tried to do this systematically has been Combo 17. Then the Cosmos survey is probably the most famous one, in which many bands have been used, and excellent redshift for all the observed objects were derived. But there are other survey charts that try to look to focus in particular that high redshift is a very deep survey. So is Alhambra, that was also a Spanish project, and PAU, the physics of the accelerating universe, which is also a Spanish project. PAU is the one that is getting to a wider area with respect to the others. All these other surveys have been, Alhambra, Cosmos, have been focusing on relatively small fields, so small fields just at most a few square degrees. PAU has extended this to a few tens of square degrees. And the goal of JPAS is to actually really try to push this to really the wide survey area, to push this to thousands of square degrees. So the goal of JPAS is to actually scan more than 8,000 square degrees of the northern sky with many, many bands, right? This is a collaboration between, as I was mentioning earlier, between Spain and Brazil. The Observatorio Nacional is one of the partner institutions, with Renato being one of the scientific director. This is the filter system of JPAS. This is actually what is the main image. So if you want one thing to remember from today's talk is really this, right? What is the filter system of JPAS? This is 56 filters, 54 narrow bands, plus 2 wider filter in the blue part and in the red part of the optical spectrum. So effectively, you're taking pictures of the sky using all these different filters. So you have the same parts of the sky photographed with all of these filters, so that effectively you can reconstruct the full spectral low resolution spectrum for everything that you're observing, not only of objects, but also of the sky. Of everything effectively that you're observing. And this has been shown that this has been designed, this filter system, precisely with the goal of getting extremely accurate photometric redshift for galaxies, with a precision that gets up to 0.3%, which is a factor of 10 better than typical broadband surveys that only have 4 or 5 wider bands. So JPAS is about to start, and it's taking place. It's going to be run from a dedicated observatory, the Javalambre Observatory, which is about 2,000 meters in the Sierra de Javalambre. This is a mountain in the center of Spain. So this is a map of Europe, and here this part is Spain, and there is a part of Spain which is particularly dark and with particularly good weather conditions. And this is where this new observatory has been built precisely with the goal of carrying out primarily this survey. So this is about a bit over 10 years ago. In the observatory there was nothing. In that mountain there was nothing. And then a few years later, a full observatory has been built with the main telescope. This one is the one that will be carrying out the JPAS. And it's the main survey telescope of the observatory. It has a mirror with a diameter of 2.5 meters. And it's a telescope designed to have a large field of view, precisely to carry out large, wide surveys. There's a field of view of 3 degree diameter with a collecting area of 4.5 square degrees. So that's the full area of the camera. And then there is another telescope, the Javalambre Auxiliary Survey Telescope, which is smaller. It's a smaller collective area. It is a 0.8 meter telescope, but it has also a very large field of view, 3 square degrees. And this is a telescope that has been devoted to carry out another survey called the J+. And before I get to tell you just a couple of slides on J+, let me mention that 20% of time of this observatory is devoted to open time. I mean, the main telescope is not yet available for open time, but will be soon. And the little telescope has been already open for the community for more than, I think, 5-6 years now. So if you have any idea of a project that you can carry out with these telescopes, you can apply for time. So these are the field of view of the 2 main instruments on the main telescope and on the auxiliary telescope. As you can see, so this is how they compare to the moon, the size of the moon on the sky. So the main instrument, JP-CAM, which is mounted on the main telescope, consists of 14 CCDs. And what will happen during observation is that on top of each CCD, there is one filter. These are represented by all these different colors. So you're effectively taking a picture of the sky with each of these CCD with one of the filters. So it's like taking 14 images in different colors for every given observation pointing of the telescope, right? And then, you know, to have a full coverage, of course, you need to tile and observe all the sky with all the CCDs, right? And this is the field of view of the main instrument on the AT80CAM, the main instrument of the 80 centimeter telescope, which has a field of view of 2 square degrees, also very large for being an 80 centimeter telescope. Now, J+, as I said, I just wanted to just very briefly mention this survey. J+ is the survey carried out with a small telescope. It consists of 12 filters, so the broad bands classical of Sloan, plus 7 narrow band and medium band filter located at very specific points to trace, for example, emission line galaxies emitting in H alpha, or the main spectral feature of stars. And it has a resolution of 0.55 arcsecond per pixel, and this is approximately the current sky coverage of J+. It's in the northern hemisphere, and about 3,200 square degrees, the DR3, will come out soon, the third data release of this survey. This is an image of one pointing of the survey. You can see here the nice big galaxies and some other more distant galaxies, and these, you know, you get these in just one pointing. Similarly, in the south, there is a twin experiment, a twin instrument, which is the T80 South. The telescope is located in Cerro Tololo in Chile. It's a project in which the ON is one of the funding institution. The PI is Claudia Mendes de Oliveira. Sorry, I realized there is something here. S+, this is another, similarly, this is a full field, and this is a zoom in a nebula. You can see the quality of the images. Despite being a small telescope, you really get really nice quality images. And S+ has a slightly different strategy from J+. There is one main survey which is very similar. It's observing large area in the 12 filter, which is very similar to J+. But then there are a few other experiments carried out at about the same time. So, or better, they are carried out. They are complementary. So, when the sky quality is not photometric, or just adding some exposure for time domain fields, or for example, the galactic survey, which is observing a region of about 1200 square degree on actually the galactic plane to study stellar physics, stellar properties of stars, like in the Milky Way. So these are the current coverage of the current internal data release, the 4th internal data release. These are the blue points as what is being covered so far. You can see here there are also some pointings along the galactic plane, and this will there is I think the 3 public data releases have been made so far, and a 4th is actually internal, and this is the link to access this data. Now let's get back to JPass. So there are these nice complementary experiments with 12 filter. JPass is really the strength of being a wider field of view, and also having these 56 filters. So a bit about the camera. The camera is a 1.2 gigapixel camera, one of the highest number of pixels camera in the current landscape of a large photometric experiment. It has a very high resolution, also 0.23 arcsecond per pixel, and as I mentioned earlier, it has a full coverage of 4.5 square degree. And this is effectively how it's going to observe. There are 4 trays of all these 56 filters. There are 14 filters per tray. And at any given time, one tray is put on top of the camera, taking images, then removed, and then another tray gets in, and so on. The depth is our target depth is similar to the one of Sloan, but with all these filters, right? Between 22 and 22.5 with all this narrowband filter. We're also observing, we'll be observing also with broadbands, getting deeper for the targets, for the object determination, for the identifying the objects, and then all these objects then are analyzed with all the 56 filters. Now the footprint, as I said, JPass is in the north. It's similar to the Sloan footprint, although a bit more north, because the telescope is a bit more north than the telescope that carried out Sloan. The survey growth is currently under revision. It's something that we are discussing at the moment, just before the survey will start. We'll prioritize a subset of the filter to cover large area faster, but the goal is to complete all this full footprint with all the 56 filters. Now here, just to have a little break from all these slides, I wanted to briefly play, but let's see if I will probably need to, for a moment, stop and reshare to play a little video that was done. It's actually a short movie that nicely tells about nicely describe the observatory and JPass itself in a bit more visual and less boring way. So I think you can see it. If you can't, let me know, okay?
It's playing.
Okay, yeah, you can see. So first of all, you can see here nice images of the telescope and the observatory. And, you know, this is like sort of like a science fiction short movie. So if at some point you want to look at it, search online. It's called Arco de Choque. Now, we are not going to see it, look at it all, but I just want to point out at some point there is a nice short description of JPass. So it's starting in a second, and I think it's a nice description of what JPass is. So now I'll shut up and let you watch.
Sí, verás, Nicole, es que he recibido unos datos nuevos en el telescopio de la noche pasada y os he pedido a las que me lo pongan el simulador. ¿Datos nuevos? ¿Ya no sabía nada? Bueno, siéntate, pero ahora voy a ver la demo de JPass, en la nueva ventana, que tiene una resolución espectacular. Andrés, siéntate. Sí, me han hablado de ello, pero no lo he visto. Bueno, es que llevan de pruebas una semana o así. Voy a leer el texto encima. Alex, lanza la demo, por favor. Yeah.
Sorry, it's starting now. I guess most of you can understand Spanish, but it also has subtitles, so.
El instrumento principal del Survey JPass es un telescopio de 2,5 metros con un gran campo de visión de 3 grados de diámetro. Tiene una cámara de nueva generación de 1,2 gigapíxeles fabricada específicamente para aprovechar todo el campo del telescopio. Y 5 bandejas donde se pueden colocar 56 filtros. Esto nos permite tomar imágenes de grandes áreas del cielo, cubriendo mucho espacio en muy poco tiempo. Al hacer 56 imágenes en diferentes bandas de la luz, podemos construir un espectro de baja resolución. Y podemos averiguar la posición y la distancia de las galaxias que aparecen en las imágenes, obteniendo así una cartografía, un mapa tridimensional del universo. Durante 6 años aproximadamente, el telescopio irá cubriendo un área del cielo de unos 8.500 grados cuadrados, obteniendo datos de objetos cercanos, como por ejemplo planetas menores y asteroides de nuestro sistema solar. También estrellas, cuásares, supernovas y centenares de millones de galaxias, alcanzando a ver objetos tan lejanos que emitieron la luz que vemos cuando el universo era muy joven. Este mapa generará una colosal cantidad de datos que será extremadamente útil para todos los campos de la astronomía. Nos permitirá descubrir millones de objetos del universo y, aún más importante, ver con gran detalle las grandes estructuras del universo y poder estudiar a gran escala la materia y la energía oscura que componen aproximadamente el 97% del universo y de las cuales todavía no sabemos prácticamente nada. Bueno, ¿qué os parece?
All right, yes, what do you think? Well, let me go back now to the slides. Yes. Okay, I think you should see them now again in full mode. If you don't, Renato, tell me something, okay? So, as I mentioned earlier, the goal, the JPass has been designed to get accurate photometric redshift to effectively do these 3D maps of the universe, 3D map of galaxies, position on the sky, and then on the third dimension on the redshift position, right? To study the clustering, the distribution of galaxies, those obtain information on dark matter and dark energies. The goal is to get 90 million galaxies between luminous red galaxies and emission line galaxies with this precision of about 0.3%, which is what the target photometric redshift precision, which is what will allow to do really this clustering, high precision cosmology clustering analysis. We also expect to get 2 million quasars and hundreds of thousands of Lyman alpha emitter with similar redshift precision. And on top of that, hundreds of thousands also of groups and clusters that also are really important and powerful for cosmological studies. But this is just for cosmological study. But if we talk about galaxy evolution, we don't, for galaxy evolution study, we don't need the same redshift precision. A bit larger errors are allowed. And in this case, with 1% redshift precision, the forecast is to get 64 million red and 200 million blue galaxies, and with larger redshift uncertainty up to almost 500 million galaxies. So really, really large samples, unbiased, with which really pushing what is the galaxy evolution, at least up to redshift to 1.5, and then at much larger redshift with emission line galaxies, with quasars and Lyman alpha emitters. Now, JPCAM, which is the main instrument, had the first technical light already 2 years ago. Then, with the pandemic and other technical problems, things got a bit delayed. Now the commissioning is finally finishing and the survey should start soon. Nevertheless, it's not that we were not busy. We actually kept ourselves busy with a very small data set that was taken with what is we call the Pathfinder camera. So it's a small instrument, one CCD camera located at the center of the focal plane, equivalent to 1 CCD of the 14 ones of the final main camera, with the same resolution, with an effective field of view of 0.3 square degrees. And with this camera, we took different observations with all the JPass filters. So the primary observations were on the extended growth strip or Aegis field. We looked at 4 pointings with all the filters. This red one is the footprint of this mini JPass, and it compares with the other project. For example, this is a pointing of the hypersuprincum. This is the extended growth strip. This is CFHT lensing. This is Alhambra. So it's overlapping with other data set. And mini JPass is what really is the data set that we have been using primarily to test the potential of JPass. This is an image, an image of actually the data, image of the data with a zoom in some interesting area. You can see here, some large nice galaxies, as well as in this other field. So it's primarily a cosmological field, which means there are no, it's not on the galactic plane, nor it has particularly big galaxies, but still enough, wide and large enough data set with which we can test the potential of JPass. The second field where we put a lot of attention is the NEP JWST time domain field. It's very close to the north ecliptic pole, and JNEP is this orange, pink orange square, and these are other observation in this area, including again an HST and also JWST observations. So this is an image of the field, which again is primarily cosmological. There are not really large galaxies, large objects, but there are a few that also can be interesting for studying also nearby galaxies. So the rest of the talk, I really want to talk, I want to discuss about JPass, present the first scientific results, and really what we concluded that, we wanted really to demonstrate the potential of JPass, right? So about the data, so the data is approximately 1 square degree. It has a total of about 65,000 objects selected in our R-band. But, if you select actually objects in all the individual narrowband filter, we get 600,000 objects. So you can think, for example, of extreme emitters in which we don't detect the continuum, but we just see the emission line in one specific narrowband. These are the depths. They go from about 22 to 23 in the narrow bands, and then we observe the field also with the 4 broadband, G, U, R, and I, and we get to about magnitude 24 for all the broadbands. The condition, the PSF is not as good as we aim at getting it for JPass, but for this mini JPass, we had to observe quickly, so we also allowed observation in not perfect night. But still, the quality of the image is really good, in particular in the broadbands, where broadbands were given priority to observing in the best nights. But in general, for all narrowbands also, the image quality is between 1 and 1.5 per-second. This is the completeness, the number density of sources, number of objects per square degree as a function of magnitude. Point-like sources, of course, more numerous at bright magnitude, and then at faint magnitude, extended sources of galaxies become more numerous. We have about, a few tens of thousand galaxies and a few thousand stars, with a completeness that is 23.5 in the R-band for point sources and 22.7 for extended sources for galaxies. These are nearby, these are stellar galactic sources. A few examples of stars from hotter to colder stars. You can see that despite, this is our mini JPass data in color overplotted on Sloan spectra. We don't have, of course, the full spectral resolution of a spectra, but the main absorption line, for example, in this case, H alpha, you can see, here you can see broad absorption features, typical of colder stars. All these features are very well observable with the narrow bands, making JPass really, really competitive for studying large population of stars, and in particular stars like metal poor stars that are very hard to detect with classical broadband, without classical broadband data. These are the first 2 papers on stellar properties, one led by Haibo Wan and one by Carlos Lopez San Juan, that focus primarily on white dwarf. We can see that temperature and metallicities, for example, of stars are estimated with very high accuracy. This is a comparison between what the temperature that is derived from mini JPass compares with temperature derived from spectra, and similar for metallicities. So really showing the potential of JPass data of our narrow bands for galactic science. the sample of stars is very limited in mini-JPass, so we're looking forward to have more data, wider data, to learn more about galactic sources when JPass is online. Now, going to the extragalactic extragalactic studies. Here are example of emission. This is an emission line galaxy, a luminous red galaxy. And again, emission line galaxy and luminous red galaxy is at higher redshift. This is a pretty local at redshift 0.07. You see the strong H-alpha emission. For red galaxy, you see the classical 4,000 Armstrong break, and so on. At high redshift, we see again H-alpha emission. Here, the last two objects here are examples of quasars. So at a high redshift, this is a quasar at redshift 1.7 with the classical broad emission lines, broad strong emission line. And this is a very high redshift quasar at redshift 4.2, where you see the strong Lyman alpha emission and again the carbon 4. Showing that how really quasars and in general emission line objects and any kind of object that has strong spectral features can really be detected and well characterized with JPass. These are some examples of mini JPass, or what will be JPass in the future as IFU like survey. So effectively, we can image IFU is like effectively studying the spectral properties of different components of a galaxy. So we don't need to take all the spectra of the different components of the galaxy. We just obtain it from the combination of all the narrowband filter, with advantages of having, we have low spectral resolution, but we gain in high spatial resolution. And in particular, we gain on the fact that we cover very large field of view. So we are not only observing, which is the case for most of IFU, only the central part of nearby galaxies, but also the outskirts, and also in particular the interaction with the environment. This is from the mini JPass presentation paper, this plot. It's showing a galaxy that has also been observed with the MANGA survey. The MANGA field of view is this, I don't know if you can see it well, but it's this hexagon, whereas in mini JPass is, we just see the full galaxy. This is a comparison between the half of the half-light radii. This is the in black are the JPass, the mini JPass data, and in gray is the spectroscopic data. You can see how, of course, they overlap on each other, but again, the main spectral features, like for example, the 4,000 angstrom break, are very clear in our low resolution spectroscopic data. And this is an SED fitting. This, in this case, is the age of the stellar population as a function of distance from the center, derived for mini JPass. This is the red and blue points with different codes of SED spectral energy distribution fitting, compared with the MANGA, with the analysis of full spectroscopic data, which are the stars. And you can see that they're very, they're fully compatible. And the advantage again that we have with the JPass data is that we can get out to large distances, whereas most of IFU surveys just focus on the central part of galaxies. Bottom here is another example of one galaxy that we are studying with this IFU-like approach. This is an X-ray emitting galaxy, a nearby spiral galaxy. You can see nice spiral arms, possibly a bar. And this is an X-ray emitting object, and we are working on the study of 38 AGN and up to redshift 0.3 to study what is the stellar population of this X-ray emitting AGN and how they compare with other galaxies that don't host an active nuclei. Now, for general galaxy evolution study, what we mentioned earlier, you need good photometric redshift. This is the error on the redshift accuracy. So, sorry, the redshift accuracy as a function of magnitude. So the target for cosmological studies is 0.3%. that we reach for all the objects at a magnitude of about 21. So up down to 21, we have all the galaxies selected have a photometric redshift accuracy below so higher accuracy, let's say, smaller error than what is required for cosmology. If we want to enlarge our sample, we can go to fainter magnitude. And for example, down to about 22, 22.5, we get that half of the sample it's at the correct accuracy for cosmological analysis. This is similar, but now instead of the color is dividing in star-forming and quiescent galaxy. So in general, at bright magnitude down here, star-forming galaxies have better photometric redshift, but the quality of the photometric redshift decreases more rapidly so the error increases with magnitude, while for quiescent galaxies, the precision remains pretty much constant down to faint magnitudes. So we carried out several studies of galaxy evolution, several projects to study the galaxies within this small 1 square degree. This is the evolution of the galaxy population, a project carried out by Rosa González Delgado up to redshift 1. This is the color magnitude, intrinsic color magnitude diagram for galaxies at different redshift, up to 0.3, here at some intermediate redshift, and here between 0.6 and 1 in redshift. What you can see here, this is, the galaxies are color coded by the age of the stellar population. You recover what is partially what is expected, that redder and more massive galaxies are older than smaller and less massive and bluer galaxies. But what I particularly want to draw your attention is on the fact that up to redshift 0.3, we have a large number of galaxies in the small, really almost dwarf mass regime between 10 to the 8 and 10 to the 9 solar masses, with masses that are very well determined through this SED fitting of our spectrophotometric data. This is another study, again carried out by Rosa González Delgado, on galaxy properties in the groups selected in mini-JPass. This is a map of groups in mini-JPass, and I'll come back to this in a few minutes, with color-coded by redshift. So Rosa studied, in this plot in particular, is the fraction of galaxies, of blue and red galaxies belonging to groups or in the field as a function of mass. We recover that, as we increase in mass, in the groups, so there is a larger fraction of red galaxies, and the fraction of blue galaxies instead in the groups strongly declines with mass, while in the field this trend is less strong. We don't have the spectral resolution of a normal spectroscopic survey, so emission line objects, of course, cannot be characterized with the same quality, but we can still, study, have an idea of what are the properties of emission line galaxies with our low resolution spectroscopic data. There are two nice works led by Ginés Martínez Solaeche, who just finished his PhD working on mini-JPass data. He developed with machine learning a tool to derive the equivalent width of emission line for emission line galaxies, and even characterize and divide this classical BPT diagram, estimate whether a galaxy, the emission lines are consistent with star formation or with AGN emission. And this is again a color magnitude diagram, and now it's instead of being color coded by age, it's color coded by equivalent width of the H alpha emission, which is a tracer of star formation. And where you find that low equivalent width galaxies, as expected, are primarily red and massive, while blue and less massive galaxies are overall higher, larger equivalent width of H alpha, higher star forming. Again, you can study, given that we we observe everything. You can study how galaxy evolution depends on the environment. This is an image of the most massive clusters within the mini JPAS field. I want to emphasize that this cluster has only 2 galaxies that have spectroscopic redshift, but it has been this cluster identified within mini JPAS thanks to the high photometric redshift quality of the data that we can derive from our data. All these points are different galaxies that have the photometric redshift consistent with the ones of these central galaxies which have spectroscopic redshift. Now, Julio Rodriguez Martin studied the galaxy population in this cluster. And just to give you a few examples, this is the fraction of red and blue galaxies, a function of distance from the center. And as expected, the fraction of blue galaxies increases as you get out towards the outskirts of the galaxy, while the fraction of red and quenched galaxies increases as you go towards the inner parts of the galaxy. Yes, so now moving to higher redshift, we have quasars are more rare objects, so they're in 1 square degrees, there are only a few hundreds of them. But with these few hundreds, we were managed to test the quality of our quasar selection tools and also, the quality of the photometric redshift for quasars as well. And this work was particularly led by Carolina Queiroz, who's in Brazil, from Sao Paulo, who developed tools to characterize the photometric redshift of quasars, deriving that it's similar to this the most precise photometric redshift that we get for galaxies of the order of 0.3%. So really at the level to carry out cosmological clustering experiment. In another work that was led by Jonas Chavez Montero, we studied actually the capability of JPAS to derive black hole virial masses from single epoch photometry. So just briefly for the ones of you that are not familiar with this, so if you have a spectra of a quasar from the width of the emission lines, so the emission lines are they get wider when the mass of the central black hole is larger, because effectively it's just like based on the virial theorem. The larger is the mass, the central mass, the larger is the velocity dispersion of the gas around. So there is a way to recover the mass of the black hole from the width of the emission line, compared also with the full luminosity of the object, the continuum luminosity. So generally, this has only been done for spectroscopic data. What we tried here is to actually see if we could reconstruct the full emission line of the objects with our data and recover the black hole masses. And indeed, we found that we can recover. This is black hole masses derived from mini JPAS data, with mini JPAS data only, and this is what is being derived with the spectroscopic data. And we get a quite good accuracies with error that of course increase as we go to fainter and less massive, so fainter quasar, less massive black holes, but still we got quite good agreement showing that really we could probably do systematic analysis, statistical analysis of large samples of quasars using our data alone. This is another work that has studied the evolution of the black hole mass, stellar mass relation across time using X-ray selected AGN. These are 300 sources up to a redshift of 2.5. And what Ivan Lopez, a student based at University of Bologna, what he did was to characterize again the mass of this black hole, but also the mass of the host galaxies, as well as the star formation rate and black hole accretion rate, and try to study what would be an evolutionary model that would bring eventually black hole and stellar mass to the local relation that is found for supermassive black hole. Another interesting application is the study of diffuse light. So in this work that was recently accepted, led by Rana, She studied the diffuse Lyman alpha emission around quasars in mini JPAS, and interestingly, she found two objects. So this on top of the first one, this is another one, which have double core Lyman alpha emission, probably linked to outflows from the central black hole, showing also that this kind of analysis of diffuse emission, of diffuse light emission, can be carried out with our data. Again, I was mentioning earlier that the target for photometric redshift accuracy for cosmological studies is 0.3%. So moving to the large-scale structure, what does this mean? So qualitatively, this is in a position versus redshift space. This is the position of galaxies. The blue ones are from DIP2, so full spectroscopic redshift survey, so where the redshift is precise, and the orange points are the position on this plane from mini JPAS data. So what is their photometric redshift? And you can see that up to about redshift 0.6, there is a very good agreement between, so the stronger the points, the higher the accuracy of the photometric redshift. So there is a very good agreement. Of course, as we go to higher redshift, the agreement starts decreasing, but effectively up to redshift 1, we really have large samples of galaxies with very high accurate photometric redshift. This is showing the number density of sources as a function of redshift. Let's say the target for cosmological studies to have more a number density of object larger than 10 to the minus 4 per megaparsec cube, which we can reach very well. So with all the objects with higher redshift uncertainty, we get between 10 to the minus 2 and 10 to the minus 1 number of objects per megaparsec cube, up to at least redshift 0.8. It drops at higher redshift, and if we cut and get more accuracy, these are these bottom points, we get less sources, but still with number large enough for cosmological studies. And at higher redshift, which is not shown here, what I was mentioning earlier, we also have quasars and Lyman alpha emitters that can be used for cosmological studies. And I want to emphasize here the WIV QSO survey. This is one of the WIV projects. It will follow up 500,000 quasars from JPAS at redshift larger than 2.2, precisely to study quasars that are redshift for Lyman alpha forest clustering, but also for other kinds of analysis like IgM, intergalactic medium studies, using the absorption features of quasars in the quasar spectra. Now, to finish up, the cluster, the search for clusters. This is, I showed it earlier, this is the largest clusters that have been detected in this field. It's about 3 times 10 to the 14 solar masses. And there are 29 galaxies that were previously without redshifts, whose redshift is consistent with being members of these clusters, of this cluster. In some forecasts from a few years back now, from Begonia Scaso, she derived some from forecasts for JPAS that we would get effectively very high completeness for groups down to a few times 10 to the 13 solar masses, making JPAS really competitive. This is the number of clusters that one detect in redshift bins, in different redshift bins as a function of redshift. And JPAS would be comparable with eROSITA and LSST in terms of the number of clusters per observed as a function of redshift, thanks to the many filters, the many narrowband filters. And we try to test this now with this mini JPAS data. This is a slice. So Matteo Maturi, he ran his cluster finder Amico, which is one of the clusters finder that has been selected for Euclid, for the Euclid pipeline. He ran it on mini JPAS. And this is an example of a map of, let's say, a response map for the cluster finder at a redshift 0.24. There are 2 main objects here, one cluster here and another one here. But what is interesting is actually that in the same field where one cluster at redshift 0.24 is located, if actually we were taken, if we actually image this the same response, but at redshift 0.36, there is actually another cluster which is just behind this very big cluster. So with broadband data, these two clusters would just be overlapped. It would not be possible to disentangle because their redshifts are so close that the photometric redshift of broadbands would not be good enough to disentangle between these two overlapping clusters. But with our JPAS data, the quality of the photoz's is large enough that we can really separate in redshift space structures that are along the line of sight. This is the amplitude, or it's some sort of a proxy for mass as a function of X-ray luminosity. And this is again, the amplitude as a function of mass now derives from the X-ray flux, from the X-ray luminosity. And you can see, so 1 is like 10 to the 14 solar masses, and this is 10 to the 13 solar masses. So we really get down to the group mass, and we can select objects that have such low masses within JPAS. Matteo did the exercise also to degrade the data and bring them to the level of typical broadband surveys and compare how much the sensitivity increases thanks to the narrow band. So this is the last thing I want to show in details. This is let's just focus on this blue curve. This is the number of detection as a function of redshift with mini JPAS data. And this blue filled area is the same, the number of detection as a function of redshift, but in the case of broadband only. So if the data at the photometric redshift quality of broadband. So as you can see, the number of detection is significantly lower, showing really that JPAS can do a lot thanks in this business of cluster detection and cluster studies thanks to the narrow bands. And I want to emphasize here that we have a MOU with the Germany Rosita. We just heard a beautiful talk from Mara. And we are really looking forward. We have a few thousand square degrees of overlapping area. We're really looking forward to work together to analyze clusters, but also, of course, active galaxies, strongly X-ray emitter, combining optical and X-ray data. Now, all this data have been public for more than 2 years now. So you can go to the JPAS website in the data portal. If you go to the Sky Navigator, you get to something like this. This is the footprint of mini JPAS. You can put the mode that gets you to see all the individual objects, the individual detection. You can click on any object. This is just a random one that I picked for these slides. And then you can click on it and get the full magnitude versus wavelength, the full pseudospectra. And then if you get more information, you can get all possible information about any objects that you find that has been selected, as well as this portal is linked to other databases like NED and the SDSS database. So you can also quickly get to other databases and study all the objects that you are interested in. So I'll just finish up. So just to summarize, I think I'm fine with time. JPAS is a multi-band wide spectrophotometric survey of the northern sky. The main instrument, JPCAM, is currently finishing commissioning and soon about to start taking finally scientific data. And we have improving the scientific potential of JPAS with the mini JPAS data, which are publicly available. And since about a year, we also have data on the NEP field that are for internal analysis, and probably next year will also be also released. But let me also mention again that now there are also large areas of the sky, the northern and the southern sky, observed with 12 filter with J+ and S+. They're not as deep and not with so many bands as JPAS, but they're very interesting data sets. And I believe actually people at ON are also very involved in both this project. So, if you haven't started looking at this data, please do soon. It's fun. And thank you.
Thank you, Silvia. It's a very nice talk.
Thanks. Again, good data.
No, but I thought it was a nice usage of the movie that we had for such a long time. This Arcos de Choque. It was a pretty nice, very didactic, pedagogical.
Yeah, I think it explains it very well. Yeah, in a very more intuitive way.
Okay, so let's open for questions. Okay, we have a congratulations to Silvia by Paulo. Chat.
Don't be shy. I think also Smara, well, I imagine, Renato, you advertised the survey quite a lot in the ON, but also as Mara mentioned for Rosita, similarly, if you have any project, any idea of, any specific idea that, to use this data set, also in combination with other data sets, feel free to message us, to send us an email and, try and propose projects, right? Different projects are welcome.
Okay. So, Andreas?
Hello, can you hear me?
Yeah. Hi, Andreas.
Hi, Silvia. Congratulations for your nice presentation.
Thank you.
My question is related to what you just said. So what do you think? We have that like JPass, JPlus, S+, but we'll have other service as well. Some photometric service, other spectroscopic. But how do you think JPass will benefit from other or help other service to improve? Not just a way of competition, but a collaboration, a broad collaboration between using data that is produced from JPass in combination with other services as well.
Thanks, Andres. That's a very nice point. Because in general, there seems to be, competition between surveys, but actually each survey is pretty unique. So there are, each survey is bringing something different to the community, right? And in particular, I think JPass is quite complementary to many other experiments that are carried out or are thought for the next few years. JPass is the only survey really that does this multi-band. So it has the advantages that you can, so for example, just to give an example, right? I was mentioning earlier this WIV QSO survey that really relies on the target selection, on a very accurate target selection that is only possible with the JPass-like data. Selecting quasars is not easy in broadband. So it has been done, of course, for Sloan and BOSS, but a lot of, let's say the completeness, the purity of the targets was not, it was a difficult business to get to very high purity. Whereas for JPass, we really get very, very accurate target selection. So not only for quasars, but you could imagine this for many other kinds of objects. So JPass can really be used to efficiently select objects that then can be studied in more detail with spectroscopic follow-up. At the same time, for other surveys that are already studying objects with spectra, for example, or with a much higher resolution imaging, having larger field of view, which is the case, for example, of JPass, that's of course also very interesting, right? I was mentioning, for example, the IFU approach of JPass, but you also could imagine, combining manga data with JPass data and getting the high resolution spectra for the center, but then study the global properties of the galaxies and its environment using JPass data. Or in the case of clusters, right? Clusters, JPass is really good to detect clusters down to group masses. We have good photometric redshift. That it would be great in combination with lensing studies, other imaging in which you have perfect, excellent image qualities, but you don't have the same spectroscopic, redshift accuracy as JPass to, for example, disentangle between foreground and background galaxies. So I think JPass is really complementary to many, many other experiments. I hope this answers, Andres.
Thank you.
Thanks.
Okay. Any more questions? Silvia, I was wondering if you could briefly mention the different missions. Well, Mara already said a lot of details of the Rosita on how to participate, but the ones that JPass currently have, or probably have in the future.
Right, so our primary collaboration at the moment are with Weave and with the Rosita. We are discussing a lot also with Gaia, what can be done together in the two data sets for galactic studies, as well as with Euclid. But also, you know, I mentioned we have this data set in the NEP, in the North Ecliptic Pole, which is an area that is that has a lot of other data from many other wavelengths. And also the JWST we repeatedly observe for time domain studies. So we are in the process of also starting a very close collaboration with this team that is working on this specific field in the North Ecliptic Pole. And if I'm forgetting anything, Renato, of course, if you are free to add things.
I'll just add that for those who don't know yet, there will be a meeting, JPass meeting in December. There will be hybrid, so people can participate remotely as well.
Yep. We also have ongoing discussion with other radio surveys. You know, it's interesting to look at the sky also with radio, and in particular, again, for active galaxies, but also, you know, in general, galaxies up to redshift in a relatively nearby universe up to redshift 0.3 or 0.5. In particular, we've been discussing a lot with Aperitif survey. So there is a lot of complementary data sets that we're, you know, other surveys that we're working together with. Yeah.
Okay. Oh, there's one. Is there a question? Yes, Simone, please.
Silvia, is there already any plans for a data release, for the public data release? It's like a J+, they have a data release for each, every time they reach 1,000 square degree observed and reduced, we have a data release. So for JPass to be more or less the same, or?
Yeah, I mean, it's actually something that we need to rediscuss and finalize. There will certainly be some data release, public data release, probably, I would imagine before then. So when maybe we will have a few hundred square degrees, but it's still something we have to rediscuss, I think, exactly how to do. But certainly there will be periodic data releases similarly to J+. Yeah. Thanks, Simone, for bringing this up. This is interesting for people.
Okay. Any more questions? Well, if not, I'd like to thank Silvia again for taking the time.
Thank you.
This talk was a very nice talk.
Thank you. All right. So bye, everyone. And I guess you're on to the next one, right?
Bye-bye. Thank you.